You open a jar of peanut butter. It looks perfect, smooth, thick, stable. But leave it untouched for a few days and something strange begins to happen. Oil rises to the top. The texture starts to change. The structure slowly weakens. And that's not an accident. Inside every jar of peanut butter, something is constantly trying to separate, break apart, and ruin the texture. And the entire factory process exists to stop that from happening. Because peanut butter isn't naturally stable, it doesn't want to stay smooth, it doesn't want to stay consistent, and it definitely doesn't want to look identical in every jar on every supermarket shelf. Today, we're going inside the peanut butter factory, and by the end of this video, you'll understand exactly what manufacturers are preventing inside every single jar, and why, without that control, peanut butter would fail long before it ever reached your kitchen. Let's begin at the source. Peanut butter doesn't start as a smooth paste. It starts as a biological product, unstable, oil-rich, and unpredictable. Raw peanuts contain nearly 50% natural oil. That oil is not bonded to stay in place. It naturally wants to separate. And here's the problem. If you simply crush peanuts and jar them, the oil will slowly rise, the solids will sink, and the texture will collapse.
So before factories can even think about smoothness, they have to solve instability at its source.
But instability doesn't begin in the grinder, it begins much earlier. Before grinding, peanuts are roasted in massive industrial ovens. This isn't just about flavor. Roasting changes the internal structure of the nut. Moisture levels drop, cell walls weaken, oils begin to mobilize. And this is critical because the way oil behaves during roasting will directly affect how it behaves months later inside the jar.
If roasting goes slightly wrong, the separation problem becomes impossible to control later.
So factories monitor temperature curves, time exposure, moisture loss percentages, because texture control begins here. But even perfectly roasted peanuts are still unstable. The real battle begins when grinding starts. Industrial grinders don't just crush peanuts, they reduce them to microscopic particle sizes. And this is where physics enters the story. The smaller the particles, the easier oil can distribute. But grind too fine and heat builds up. Too much heat accelerates oil migration.
Factories are walking a tightrope. Here, too coarse, it separates. Too fine, it destabilizes.
So they use multi-stage grinding systems, primary crushers, intermediate mills, final high-shear refiners, all designed to control friction, heat, and particle consistency. But grinding alone doesn't guarantee stability. Now comes the silent adjustment. Here's something most people don't realize. Commercial peanut butter is rarely just peanuts. Salt, stabilizers, sometimes sugar, but more importantly, emulsifying agents. These ingredients are not for taste. They're there to slow oil migration.
Without these microscopic stabilizers, most jars would separate before reaching the store shelf.
Factories carefully calculate fat percentage, solid to oil ratio, viscosity targets, because consistency isn't natural, it's engineered. But even perfect formulation isn't enough. Now the texture must be controlled at scale. After grinding and formulation, the mixture enters industrial mixing tanks. These aren't simple blenders. They use high shear mechanical force to disperse oil evenly, eliminate micro air pockets, create uniform suspension.
This is where the smooth you recognize is actually manufactured.
The mixing stage determines spreadability, mouthfeel, resistance to separation, and this must remain consistent across thousands of jars per hour. But here's the twist. Even perfectly mixed peanut butter is still trying to separate, so factories move fast. After intense mechanical mixing, the mixture is warm. Warm oil moves faster. Warm oil separates easier. so factories rapidly cool the mixture before packaging. This controlled cooling increases viscosity, slows oil mobility, stabilizes the internal structure.
If cooling is delayed, the internal structure weakens before it even reaches the jar.
Temperature control here can determine shelf life. And now we reach one of the most underestimated stages.
Peanut butter is now smooth, warm, and structurally balanced, but it's also fragile. At this stage, it behaves like a semi-solid suspension, a mixture of oil and microscopic peanut particles held together by controlled viscosity. Now it has to travel through stainless steel pipes, across pumps, into high-speed filling machines. And this is where another risk appears. Peanut butter doesn't flow like water. It behaves as a non-Newtonian fluid. That means its viscosity changes under stress. Push it too hard, and internal particle alignment shifts. Apply uneven pressure, and oil can begin migrating microscopically before the jar is even sealed.
The very act of moving peanut butter can start the separation factories are trying to prevent.
So, engineers control three critical variables during transfer. Flow rate. Too fast and shear stress increases. Too slow and temperature drops unevenly. Pump pressure. Industrial positive displacement pumps are calibrated to avoid turbulence. Turbulence creates air pockets. Air accelerates oxidation. Temperature stability. If the mixture cools too early inside the pipeline, viscosity increases unpredictably. That affects fill consistency. Now comes filling. High-speed automated lines can fill hundreds of jars per minute. But here's the tension. When peanut butter drops into the jar, it cannot splash, it cannot trap air, and it cannot disturb internal distribution. Even small air pockets can increase oxidation risk, create visible surface defects, trigger faster oil rise over time. So factories use precision volumetric piston fillers, servo-controlled dispensing systems, anti-drip and bottom-up filling nozzles. Bottom-up filling is critical. The nozzle enters the jar and fills from the base upward. This minimizes air entrapment and reduces structural disruption. If filling is slightly inconsistent, two jars from the same batch could age differently on the shelf. After filling, jars immediately move to capping. And this isn't just about sealing. The cap must prevent oxygen entry, withstand internal pressure changes, maintain vacuum integrity. Some facilities even use nitrogen flushing before sealing to displace oxygen and slow oxidation, because oxygen is another silent enemy. Finally, jars pass through vision inspection systems. High-speed cameras check fill height, surface texture, lid alignment, structural uniformity. Any jar showing visible oil pooling, surface collapse, or abnormal air pockets is automatically rejected. And only after surviving mechanical transfer, pressure control, oxygen management, and structural inspection does the jar move forward. But the battle still isn't over, because once it leaves the factory floor, gravity starts working again. And that's where the final defense comes in. Before large-scale distribution, samples are stress tested. They simulate heat exposure, vibration, long storage periods.
Factories intentionally try to make peanut butter fail so it doesn't fail in your kitchen.
They measure oil layer thickness over time, texture degradation, oxidation levels. Only when it survives these tests does it move to distribution. Remember the promise. Inside every jar, something is constantly trying to separate. That something is simple physics. Oil is lighter than solid peanut particles. Given time, gravity wins. Peanut butter is not naturally stable. It is temporarily stabilized. What factories are really doing is slowing down the inevitable. They control particle size, oil distribution, temperature, viscosity, molecular interaction, all to delay separation for months. Without that control, your peanut butter would split, harden,
oxidize, and lose its texture long before it ever reached your kitchen. And now, the next time you open a jar and see that smooth surface, you'll know it's not natural, it's engineered.
If you loved uncovering the hidden engineering behind something as simple as peanut butter, this channel is where everyday food gets decoded. Because once you understand how factories control instability, you start seeing every product differently. From oil separation to microscopic particle design, nothing on a supermarket shelf is as simple as it looks. And this is just one jar. There are hundreds of everyday foods hiding systems just as complex, and we're going inside all of them. So subscribe, turn on the bell icon, and stay with me as we break down the industrial logic behind the things you use every single day. Because the more you understand how things are truly made, the harder it becomes to ever look at them the same way again.